So while I'm doing that, welcome everyone. We have a fairly packed schedule. I'm assuming all the speakers are here, although Zach, your request to switch the order is no longer necessary, I believe, correct? So I think we just want to dive in then with all the presentations that people have prepared, assuming they've prepared them, and then we can conduct a conversation. I think it'll be pretty free-flowing. There's 20 of us, on what we've learned around these infrastructures. So with that, we'll start right now with Alicia Garmulowicz, who's at Santiago, Chile, talking about Materium. So let's see if you can share your screen and find out what happens.
Thanks very much. Thanks, Jim. Thanks for everyone for the opportunity to present today. I will just share my screen. So, everyone see?
Yes.
Great. Just get this out of the way. All right, so I'm going to talk about my applied research areas of Materium. And as Jim mentioned, I'm a professor at the University of Santiago in Chile. I'm Canadian by background, so I prefer in English than in Spanish. What we're providing here is an open platform for biomaterials development. Materium, we call it Nature's Recipe Book, is focused around materials made from naturally abundant ingredients, so biopolymers and common minerals. And the inspiration is really focused on imagining if our circular economy was fed by the ingredients, the materials that we find all around us. So if you look into, the natural world, you see that waste is a resource, right? So looking at the circular economy as the focus and motivation for our work, we're looking at how can we develop infrastructure and manufacturing whereby materials that are in circulation are nutrients for the natural world and go back into nutrients after end of life. And so the mission that we have in order to open that world up is to enable more people in more places to participate in that next generation of materials. And to that end, we develop open recipes and data on materials made from abundant sources of these natural ingredients. And one of the kind of main themes behind this as well is that there's a lot of focus now from the plastics waste crisis that we have on our hands to look at alternatives that are biodegradable, et cetera. And what we're looking at is a more distributed supply chain model in order to enable us to develop manufacturing and production models using natural sources of biomass, because it doesn't really work the same way as concentrating large amounts of petrochemical production. When you look at specifically distributed sources of biomass, specifically from secondary sources, so primary sources being from, say, for example, corn that's grown from in arable land, et cetera, that competes with food sources as well as water irrigation, et cetera. We're looking at more secondary sources, which are food waste, agricultural byproducts, aquaculture byproducts, et cetera, which are plentiful and are underutilized in today's economy. So that more distributed level of biomass, which is everywhere there is consumption, that requires a more distributed model of supply chain development. And so that's the kind of DNA, I suppose, of how we need to open up this type of information for more people in more places to enter into production of biomaterials. So this is the team. I won't go into detail today, but we're growing all the time and focusing a lot on a combination of 1, material development and design, 2, green chemistry or life-friendly chemistry, and then 3, an open data infrastructure development model fed by open source testing for biomaterials as well, which I'll get into in a bit. Supporters are varied from the circular economy world and the research world and design as well. And so here I'm going to just transition quickly to look at our recipe library to give you a sense of what we're doing. And then I'll get into the data infrastructure side, which is touches more on in the RDA world. First of all, the recipe library, just to give you a sense of the what we've done to date. And we're a very young platform. It's been around 1.5 years now. As you can see here, you can search by ingredients or recipes and by different biopolymer constituents, so to speak, the ingredients themselves. So by carbohydrates or sugars or proteins, etc. And you can see, you can click on a recipe, for example, this one, a cornstarch bioplastic. This is uploaded just recently by a user. And so anyone anywhere can submit a recipe. And as you can see, it's very much like a cooking recipe. You see the ingredients, the proportions, and the steps to make it. And so the idea of this being open source is to enable more people to accelerate their R&D process. Open source, we're not saying is the be all end all, but rather it enables more people to get in the game, so to speak, and take a recipe from the commons, develop it with their own process, etc., and then enter into the commercial space. And whether they choose to keep that recipe open source or not is their prerogative, but the aim is to have that data layer that will enable that development in more places. So the recipe library is what we've kind of launched with. The second part that we're very close to launching in the next couple months is what we're calling the data commons, data sandbox. Our data commons, the idea is to provide property information on the biomaterials that we are developing. And that will be a range of properties from mechanical properties to thermal and barrier properties, et cetera, aesthetic as well for the design community. And that kind of envelope of property data is pretty open in terms of what the community demands. So that's also the second part. And then the third part I'll touch on just briefly is that we're looking at more of a community hub approach, whereby working through labs that have roots in their own local markets for material development, understanding the market needs in terms of bioplastics, etc. And so actually physically making materials and having that kind of decentralized hub model is our aim. In terms of impact, we're looking at obviously circular economy being an overarching theme. Resilient supply chains is coming more and more to the fore, especially with COVID being a very good case in point, whereby supply chain resilience was shown to be not there in a lot of cases. And so developing more local and regional material supplies is actually quite important, not only from a circular economy perspective of being able to circulate nutrients more effectively, but also from a resilience perspective when shocks to the system happen. And I mentioned accelerating innovation. Current projects, we've got funding at the moment from the EU Commission through the Horizon 2020, and we have a few different partnership agreements or collaborations, I should say, that we're developing at the moment. One is through the University of Oxford on machine learning approaches to biopolymer prediction and modeling, and in connection with the Center for Bits and Atoms and NIST, the project on expanding materials modeling, measurement, and design through open material testing technology. All right, so the roadmap in general, the data development side, we're focusing on the moment. The experimental side, we've been developing a first couple data sets through my research group at the University of Santiago, focusing on seaweed biopolymers that are plentiful in the region, in Chile in general, because of its large coastline. And we're looking at developing generalized recipe portfolios. So basically taking one recipe of one set of ingredients and then having variations compositionally as well as process-wise in order to create a portfolio of variations that have different performance specifications. So here you can see our Agar bioplastic data set. You can see a range of tensile strength versus elongation at break, benchmarked with different conventional polymer systems. And as you can see, the range is quite large. This is only varying composition. So it's a very simple material system, agar, glycerol, and water. But you can see a range of properties that's quite interesting. And our aim here is to start to develop more polymer systems from more research groups, as well as our own development in order to apply more sophisticated machine learning algorithms, et cetera, to have generative models and assisted learning, et cetera, to be able to guide the community, as well as kind of work collaboratively on material systems to explore the property space that's possible. The scaling aspect of data, this is where we're kind of getting to now, where we're starting to, we've built the data infrastructure by and large, although that's still needing to come together for launch. Zach will actually talk a lot about the nuts and bolts of our data infrastructure in the next talk, so I won't go into that. But the scaling of the data community is really key, and we have three main angles to that. One is the use and leveraging of research groups, and we're aiming to develop a strategy on that to make the platform as useful as possible to researchers who want to utilize it for their own research, their development paths, etc. Additionally, we want to tap into the distributed manufacturing world through fab labs and makerspaces. We have deep roots there. And the interesting gap that we have identified in the digital fabrication world is that there's a huge amount of attention and competence when it comes to hardware and software development and programming, but when it comes to material making and material characterization, it's a huge gap. And so we're trying to traverse that by virtue of developing open source testing tools. That's the collaboration through the Center for Bits and Atoms and NIST. We're also looking at other means of testing materials as well. And Fab Labs often have collaborations with universities. So it's something that can be done in terms of calibrating machines, as well as working in collaboration basically to test materials that are made locally. So that's a huge gap. But if we are successful at disseminating technology for materials testing through the distributed fabrication global network, which is thousands and thousands now of labs, that could be a massive data accelerator. Imagine bioplastics and biomaterials being made with locally appropriate material systems that are contributing data and collaboratively developing the property space of material systems, et cetera. That could be a huge amount of data that could be leveraged. Oh, and I'll mention briefly in general, we're looking at collaborative mechanisms. For example, in the open software and open hardware world, specifically open software obviously has been a success in this case, is how specific community-driven platforms and mechanisms can be leveraged for enabling people that are disparate in time and space to actually contribute to a collective project. And so we're trying to develop and translate some of the lessons learned, but also adapt them to materials as well. And what that kind of open source collaborative DNA looks like in material development and design is a real experiment for us. So that's something I think is really exciting and has a lot of potential as well. This is also a really important theme, I think, for learning and experimentation. I'd love to hear thoughts specifically from this community on this, is developing data confidence. So we have three, this is, you know, the kind of flip side of openness, right? We have to make sure that the data that we have is robust and people have confidence in it. The few leading thoughts we have for developing a strategy there is one, having reference data sets whereby a material that is well characterized in a number of different humidity and temperature profiles, for example, can be used as a reference to calibrate the same material system that's measured in a different location with a different set of, with a certain temperature humidity profile. And that can be calibrated if we have all of the data in that reference data set to compare to. That's something that we need to work with very controlled settings in order to understand how that material responds to different temperature and humidity settings, et cetera. But having those reference data sets, I think, is going to be important kind of touchstone for the community. The second is machine calibration, which I mentioned a bit when we're looking at open source testing tools, calibrating it with university equipment, standardized equipment, and understanding the variation that exists in that. And then third, just a really robust data tagging system whereby people who are navigating the system will understand who developed this data set, under what conditions, what are the assumptions underpinning it, what are the standards used, and is it, you know, what confidence do they have in it by extension. And so again, that's a strategy that we're thinking about, but this is very much in development. And finally, just to touch on the data utility, we're looking at enabling better selection. So, and if someone is developing and wants to develop an alternative to packaging, for instance, from petroleum to a bio-based, they'll be able to have a selection tool whereby you say, these are the performance characteristics I'm looking for. I need this tensile strength, this water barrier property, et cetera. And then they'll be able to be queried in the system. The second is just design. So understanding how to guide the development of custom formations and composition, analyzing how the process and ingredients inputs change with specific properties. So that's the kind of guidelines for materials design specifically. And we want to enable more competence in that area and disseminate that knowledge as widely as possible. And then third is entering into production for more companies in more places. At the moment, the biomaterials space is quite concentrated in terms of a few companies who have the lion's share of the market, and it's centered on primary feedstock as well, which is has land use change emissions associated with it, as well as problems with arable land competition, et cetera. So in order to bring more small and regional players to the table, specifically with secondary sources, we need to open up knowledge and access to knowledge about recipes and entering into production. One thing I didn't mention, but is important with the data scaling, is the application of machine learning for predictive models, as I mentioned. And that's also kind of a scaling mechanism whereby in the selection tool that we're envisioning, if you want to allow for computational formulations to be in there, that will be an option. And data tagging similarly will enable you to understand whether a data set includes predicted formulations versus physically tested formulations. Okay, so I'll just close with a few sentences on the data infrastructure, and I'll let Zach color in the outlines here. We're looking at fair data principles being fundamental to the Materium ecosystem. The aspirational but important goals of FAIR are going to be implemented through our use of Cordra and our use of schema.org. And Cordra being the system that will really power the entire the infrastructure on the back end, and schema.org is really important for developing biomaterial language that we can enable other communities of practice and research to start talking the same language when we're trying to develop this large mobilization in terms of data and materials development. And we have a small demo. This is something that on the front end, you get just a taste of. And I do want to preface this. This is very much in development, but I think it'll give you a little taste of what we're doing. So this is, you'll kind of notice a similarity of what I showed you before with the materials library, but this is all new. You'll be able to see our material system. So this is the Agar glycerol water system that I showed you the Ashby diagram of. This is the future system that we're developing. So here you'll see all the variations of the recipe itself. And the properties, the aim here is to have a ternary where you'll be able to see the different compositions between the three ingredients here on the three ends of the ternary. And when you navigate, you'll be able to see the properties that are associated with those. If you add this to your personal sandbox, so the idea of developing your own personal sandbox, you'll be able to compare material systems of interest in addition with comparing it with conventional or commercial materials, which we'll be loading in. You'll be able to compare properties. Now this is just, you know, it's not really a real graph yet, but the aim is to have Ashby-like diagrams where you'll be able to see materials such as strength and yield strength or ultimate tensile strength or what have you, and elongation at break, etc. And you'll be able to click on individual points to see that specific sample. You'll also be able to understand under what conditions it was tested and look at those records and who contributed that data as well from what environment or geography. So that in the spirit of regional material development, you'll also be able to understand what mix of biomaterials makes sense in your given region and actually see that come alive with researchers or contributors in your area. So yeah, that gives you a taste. And with that, I'll close. And thank you very much for your time. And I'd welcome any questions you have and any discussion points going forward.
Great, thank you. That was a very nice overview. In the interest of time, let's keep things moving. I edited a little bit the document that Zach put a link to in the chat. If folks have specific questions, either for a single speaker or for the panel, feel free just to put those into the document. We can certainly talk, but it would be good to capture them in the document as well. So thank you. So go ahead, Zach.
Thank you. Are you seeing my screen, Jim? And do you hear me? Great.
Yeah.
So I'm going to give a summary of some work going on to build a microstructure repository. And as Licia said, the data infrastructure and data engineering part that I'm thinking about is being applied to broader efforts, including Materium, the microstructure repository under development, and a portal for high throughput experiment. But I'm going to speak here on the microstructure repository effort. A little bit of background. So NIST hosted 2 workshops that had broader goals associated with identifying key issues in materials data curation and establishing protocols and best practices for doing so. And we had 2 workshops and have started working on prototypes to meet that need. Just a quick summary of the workshops themselves. The biggest emphasis was on metadata for images and analysis and samples and instruments and so on. And I wanted to put my talk in perspective of some of the input from that workshop. So both of those workshops occurred when we could meet in person, and a lot of work happened on the whiteboard. And this is the whiteboard for describing necessary metadata for instruments. And one of the things I wanted to highlight was one of the elements was the calibration history of that instrument, that's an important aspect you need to know to understand and trust the data. Another aspect of metadata for instruments is that they typically have divisible components. Excuse me. This is a photograph of the whiteboard for metadata for samples. And I wanted to highlight that an important aspect of this is the history of the material. What material went into some sort of process, like annealing, and what was the material that came out, and capturing that entire process history. And I'm going to display on the next slide a notional sort of graph view of this information and walk through it and map the concepts of that whiteboard to a graph-based conceptual representation of metadata modeling. So one of the things mentioned in instruments was capturing the calibration history. So you can see here that metadata records and data records about calibration have linkages to instruments or instrument components. One of the other features of that whiteboard or from the workshop is divisible components. And just to give you one example, a diffractometer has many components that can be unbolted and replaced with other types, from the source to the detector to the sample stage or the sample holder, which can be custom made. With the processing history, you can start with one or more source materials that go into a process, and one or more source materials can come out of that process, and you can have data sets associated with the process itself. An example from additive manufacturing, AM powders will go into your process. You could do in situ process monitoring of the melt pool, for example, and then you have your part or test artifact that comes out of that process. And of course, once you have a material, it visits one or more instruments to undergo observation, and each of those instruments will generate one or more data sets. And this particular graph is just the view of a single step in a process. So if this graph looks complicated, it'll get even more complicated as a material undergoes many additional steps in its processing history, and you can perform measurements at various stages of material and its processing history. This is just a linear view of things that are possible. There's also parent-child relationships that one would have to capture. You could make a sample and then divide it into subsamples and do unique processing histories or unique measurements. Likewise, it could go the other direction. If you're creating a composite material or mixing the agar, glycerin, and water that Alicia mentioned, you're mixing materials together, and each of the source materials may have its own unique processing history. So these are all things that I want to capture in a data model. So the goals thus far are to support all microstructure workshop input, as well as other needs from other projects, and develop a graph-based data model for research objects. One of the things I'm doing in this project is pushing in research areas in the infrastructure itself. And some things that I really want to push on and explore are ubiquitous use of persistent identifiers for all research objects, digital object architecture and linked data platforms, specifically JSON LD, and extended implementations of schema.org. And these research areas have a pretty reasonable footprint within RDA. There's a number of groups focused on persistent identifiers or minimum metadata for certain research objects. And there's a lot of useful input to learn from these groups. In digital object architecture, there's some RDA groups and other groups, and an RDA adoption story in using digital object architecture. And lastly, I mentioned JSON LD and schema.org. So schema.org is an industry-led voluntary consensus standard centered around interoperable data and metadata on the web. And a number of science-focused extension projects have been sort of launched, sort of piggybacking off of schema.org. Some of them include bioschemas in life sciences, CodeMeta for software metadata, and this research object project, which mentions using schema.org for their metadata. So I think there's an opportunity here to join this growing group of community who are sort of leveraging and extending this particular metadata format. So that adds a bullet to my goals, and that's to just demonstrate practical use of those three things. And one important aspect underpinning all of this is vocabulary. And I think there's two general styles in which you can create vocabulary and use them within schemas in some way. And I've sort of referred to these as hard-coded vocabulary and extensible vocabulary within some sort of scaffolding. And I'm going to give examples of each of these. So in the hard-coded example, and this I think works well within a well-bounded domain, you can see in the thermal ML schema, the concept of an inchy key, or the vocabulary for inchy key is baked into the schema. Likewise, in a NIST schema for diffusion couples, the concept of a diffusion annealing temperature is baked into the schema because it's a well-bounded and confined domain. And for two-layer examples, I'm going to show both open microscopy environment and the NIST microscopy Nexus schema that's available at data.nist.gov. And both of these have similar patterns for sort of an open-ended use of vocabulary, in the sense, looking at the NIST Nexus parameter type, a parameter can have a value like a number or a string associated with it, and a name and a unit to go with that number. So this is an example of having fine-grained vocabulary that's sort of decoupled from the underlying syntactic representation of the schema. And this is the design choice that we have chosen, such that vocabularies can grow and be responsive to needs within the effort. So I'm using a 2-layer vocabulary. The lower layer is based on a lightly extended version of schema.org, where I'm trying to minimize the number of new properties, i.e. terms, but there are some new types. And the upper layer vocabulary is based on an instance of schema.org's defined term with some additional SCOS vocabulary to enable mapping between terms. And this is something that I anticipate being expansive and growing, in the sense that if a vocabulary exists in a spreadsheet, I'm importing it and normalizing it and mapping it to other vocabularies. Just to give a simple example of this in use, here I'm showing 2 example JSON LD objects. Both of those are data sets, and they have a property in them called measurement technique. So both of them are of type data set, but when you look at the measurement technique, one of them is diffraction data set, and the other is a scanning electron microscopy data set, such that you can have sort of tiered levels of interoperability, such that clients can sort of view, hey, yes, this is a data set, and I know how to consume a diffraction data set, as an example. This is an example not using PIDs. The font size is going to get a little smaller with an example showing PIDs. So here's another, and this is the backend representation. This is the thing that is going on in the backend, and the thing that clients might consume might be a little bit different. So this is another data set, and you can see a lot of sort of cryptic strings that represent pointers to other objects in the data platform. If I highlight one in particular, the measurement technique, it's a pointer to a defined term of transmission electron microscopy, and that object of type defined term is in a defined term set, which is yet another pointer to another object of type defined term set. And that defined term set is the NIST Materials Resource Registry vocabulary. And I have a DOI to the source document that was slurped in to populate those set of defined terms. So one of the things that I'm pushing on is making our vocabularies themselves fair, in the sense that a term meets all the same criteria of findability and accessibility and use of persistent identifiers, such that you could trace a term back to its origin. Some of the other PIDs in this record is an internal PID describing the specific sample, an internal PID describing the specific instrument, i.e. the specific instrument potentially housed at a university or a laboratory. Under the variable measured, this is for things like material properties, much like that parameter schema that I showed from Nexus. This has the same design pattern where this value has a property ID associated with it, which is mapped to the concept of average grain size. And the unit code is mapped to a PID for the unit of measurement of micrometer. And I'm looking forward to some of the other work going on in the space of fair representation of units. And I hope to swap out sort of this local representation or PID to a potentially global one. There's a lot more detail I can go into, but I'd like to end here and thank everyone for their time.
All right, thank you very much, Zach. That was a very nice overview. A lot of stuff was already flowing into the Google Doc, so thanks to everybody for their comments. So give me just a moment here. I think Mikiko's next, but this is the risk of having too many windows open. Yes. So Mikiko, if you're available to share your screen, I didn't check to see if you're on the call. Yeah, there are her slides. Very good.
Do you hear me and do you see me?
Yes, yes.
Okay, good. Nice to see you all, and perhaps some of them nice to see since a long time ago. I'm very pleased to be in Costa Rica in a virtual way, and very happy to share hope and pain and the future vision through the Materials Data Platform, which we just released in June this year as DICE, with metadata schema and vocabulary trials and the repository MDR. And just in case, as you know perhaps very well about NIMS, but our division, MADIS Research and Service Division, and our center, Materials Data Platform Center, launched 2017, so some of them may not yet know well. Therefore, I'd like to introduce my colleagues with a Facebook. And the division, MADIS, consists of these research groups. And for example, sorry, oops, where's the razor pointer? It is. Dr. Togo is going to show up after me. And Takuya here and Asahiko here are helping me today. And Kosuke is also helping me today. And we are about 66 people who are involved in this slide data structure, modeling, curation, collection, mining, and infrastructure itself. Now, we are on the third year of this materials data platform project. Now we called DICE, and consists of 4 important components: the creation of the data, for the use of data, and store the data to publish the data. The slide, this one is very simple and nice, but this one for details is too very, very, very complicated. As you see that on the left-hand side, building advanced data sets and data collection together with large-scale facilities to collaborate for different type of data sets, to storage and manage and share with proper policy on a server to be able to use for analyzing and material simulation for materials development. And the platform to share is a material repository, one for the open data for publishing, and the other one is a closed data repository for between industries. That's a sort of components. So I would like to describe let one as a data provider, the researchers as data provider, and we as a data center, and for the data science for academia, and some of them work with private sectors. And for the next year, a new project that we are trying to reach to government heart is to aim to data cloud for materials as a data hub for Japan. Now, to mash up between the simple platform components, we have this number of square are the services, and the services are connecting each other. So the question is how to connect each other. So to connect these boxes, we ended up to spend 3 years to design common data metadata model, and progress and backwards and sideways. And then this is the most beautiful drawing, the metadata set that Asahiko involves so much. And most important part is, of course, primary parameters, as Zach mentioned. And these type of groups, we are working with the research groups in this department. And also we designed a common message format to communicate with other square boxes as single services. And for example, experimental data files and metadata sets go through a data collection system which is another box. So how to communicate between to the research data management, and then we provide a common metadata model. There's a long battle between this system owner and this system owner, but we come to agree to share the same metadata model so that be able to come to the MDR. So we published this metadata list and also some guidelines or recommendation on our homepage. Particularly some universities sort of contacted us what metadata schema would be recommended if we want to run a smart laboratory concept in universities. So, however, there's a very more at a deeper level discussions that then researchers obviously cannot cope with such detailed description by using their time. So we decided to put all that, the rest of data, which is as a primary parameters, as I shown here with JSON LD file. And also we ended up that then we need translator, how to translate from a different data resources. And then we created a Wikibase, which called MatVoc. And MatVoc is currently internally a vocabulary service to help translation between different data sources, and also for users who deposit data to repository, or the people who want to export data for their own work. So this blue area is a very important key service to connect and for the fairness of the data. And currently we look at the NIST as a standard of everything in materials vocabularies. So we imported your idea onto our wiki and to manage as a MatVoc. So vocabulary-based metadata, if we could reach to, and then we finally can translate between data collection service and common message by using common message format. And but of course, with API query, we can transfer query to search what data in the data repository and where does it come from and what recipe that data were produced with. So by having this sort of vocabulary infrastructure, we have also developed the how to connect instruments at NIMS, which is currently now up to 60 instruments by wireless or by wire to the IoT server. So once the researchers connect their instruments, then agree to follow that metadata schema in some level, and then a data sets come to IoT server, and then which goes to a data management service, and then goes to storage server. That's the story that I like very much, and I hope that the NIMS research can cope with this, share with this happy story. So far, what's happening to our data collection system is that we obviously are quite aware of that. Normally, experimental data are not readable by human and machine at the first stage. So translate binary to text format, and text format to readable data, and readable data to visualizing to what this data set means to users. So this red process are now launched as a system together with some way of translation to machine readable manner. So those data sets are binary to format conversion and readable to auto-analyze visualization is also require certain level of metadata. That's why, which I mentioned just a few seconds ago, that data conversion tools is one of the important tools for researchers, which we publish at github.com. the last stage is then after we collect the data, and then how to share the data or publish the data. So that's the materials data repository function to do this. And mdr.nims.gojp are currently encouraging NIMS researchers to submit their publications and hopefully to get with data sets, hopefully by following the standard metadata schema. And if they could do that, and then MDL can function to show as a NIMS research directory service by human name, and also data sets management on research data management that we use. We release this one with open source framework to working together with National Institute of Informatics. So in summary, DICE has this number of systems, and then some parts are released and some other parts will be released to next year. So materials data platform aiming to variable platform and also public service as well as internal services, and R&D platform for academia. And most importantly, we work with some companies who has the same desire to how to collect and manage the data in each companies to be understandable by launching academia finding. And DICE aims to Japan-wide data hub next year. And then obviously we perhaps be able to provide a library or data models, metadata schemas, and also recommend some level of recommendation how then we can share the data if you follow by the standard schemas. So I'd like to special thanks to Takuya and Kosuke and Asahiko, and two of them are joining today, and then my colleague Hideki Yoshikawa. Thank you for joining me.
Well, thank you very much. Wow, it's quite a bit of an accomplishment that you've achieved since we last talked. So it's very exciting. So thanks for that overview, and I'm sure there'll be more questions, if not just now, perhaps down the road too, because there's a lot to unpack there. So our next presentation, I believe, is from your colleague. Let's see. Oops, that's the wrong link. Oh boy. Oh, there we go. Sorry for the delay. If you know you're speaking next, go ahead and put your slides up and I'll do the proper introduction right now. So it's Atsushi Togo on Phonapi?
Yeah.
Phonapi? Phonapi?
Yeah.
I don't know. You can tell me how to say it. Right? Phonapi.
Okay, can I start?
Yes, you must begin. Thank you.
Yeah, can you see my slide?
Yes.
And, can you hear me?
Yes.
Oh, good. So I'm a computational material scientist at Shitogo from NIMS, Japan. And I develop a software package called Phonapi. And I'm not a specialist on data. I'm a person who produce data using computer simulation. And this is today's outline. I first explain what is computer simulation. And next, I talked about a little bit mathematical modeling for phonons. And lastly, I explain some implementation of the code or what can be done. Can we do using a Phonapi or something like that. So Phonapi is a software package for phonon calculation, and in the material science field, it's widely used worldwide. This year, the number of citations will be like 1,000. And using this, we can get some crystal property of atomic vibration. Atoms are always vibrating, even at 0 Kelvin. And from that information, we can get the heat capacity or thermal expansion and so on. And this software package can be obtained from internet. It's developed under open source license. And it's written in Python, and it's quite easily installed using the pip or conda or something like that. And PhonoPy cannot work only by PhonoPy, and it requires some external atomic force calculator. And for the atomic force calculator, I usually use a fast principle calculation code. For that, PhonoPy has an interface to those atomic force calculators. For example, BASP code, cache step, or something like that. Not only the fast principle calculation code, but the interatomic potential code, empirical potential code like lumps, something like that. And it has API. And this is a problem for me always. Often experimental people said computer simulations are not real. But the only experiments are real. But fortunately, a researcher using molecular dynamics simulation, molecular dynamics is like this. The atoms are something vibrating that you can run the calculation and analyze the results statistically. And then it's a kind of Newtonian, solving a Newtonian equation at the time step. And they claim their research is real. They said to me because they thought my phonon calculation is not real, but at least a computer simulation can be real. It's a good news for me. And yeah, but sometimes I don't understand well what is computer simulation. So I went to Wikipedia, and Wikipedia said computer simulation is the process of mathematical modeling. And it's performed on a computer, which is designed to predict the behavior of physical system. In our case, it's phonon atomic vibration. And in our case, we implement it like this. We describe equation of atomic vibration and translate it to a code. And with a crystal structure, we put them into a computer. Then we get the data as a physical property. This way, my computer simulation works. And then we need mathematical modeling for phonons. And first, we have to define a crystal model. So always we need to define carefully some model, physical model. And the crystal model is like this, atoms like this. This is crystal, and this is atoms vibrate in the vicinity of the equilibrium positions. So some little displacement from the equilibrium position is allowed. But like the lithium-ion battery, lithium can migrate like this. This is not allowed in a crystal model. And all the atoms are connected by a string each other. So under this model, we have a crystal potential energy. And it is expanded into a Taylor series with respect to atomic displacement. So some little displacement from the equilibrium position. And at the coefficient, we get a force constant in the real space. Higher order terms are ignored, then we get only the second order term. And yeah, but we want to get this second order term to get the phonon information. For that, we solve this equation. So this is atomic force is the first derivative of crystal potential with respect to atomic displacement. And also with atomic displacement, we should be able to solve this equation. And this force is computed using a fast principle calculation. And this displacement U is a displacement inside of the atoms. And this is provided as a crystal model to fast principle calculation. Then we can get this force constant. And then what we have to do is to transform the force constant, its spring constant, in a direct space, real space, into phonon space. First, we transform using Fourier transform into a reciprocal space. Then again, we transform it into a phonon space using a unitary transformation. Then we get this unitary transformation means the eigenvalue solution, and we get the phonons as the eigenvalue solution. And the eigenvalue correspond to a phonon frequency squared, and the eigenvector correspond to a phonon polarization vector. This is the result for silicon. And this is the horizontal axis for wave vector, and for the vertical axis, it represents a phonon frequency. And this line curves is called the dispersion relation. It is discretized because we solved this eigenvalue problem, and this D is emission. So this phonon frequency squared is real value. And this Q represent wave vector, and the nu represent phonon branch. So it's a solution, discretized solution index. This way we get the phonon frequency. But why we have to transform the information from real space to phonon space? That is because this information can be directly of the measurable.
安全管理室よりお知らせします。本日、緊急地震速報の受信、地震発生に伴い火災
It's a training to escape from building when the earthquake happens today. So unfortunately today.
So it's just training though, right? You don't have to leave?
I have to do, but this year because of COVID, so the only some number of people have to do that, but not for me. So.
Oh, the good news, because I get in trouble if I stayed inside. So we can wait.
I am sorry.
Fire and earthquake drill will be held today. But in order to prevent infection by novel coronavirus, we will not conduct evacuation drills for all the staff this year, for avoiding close contact and forming crowded place. For instead, please be sure to download and read the text of the fire and disaster prevention course on the DeskNet's information announced today. Thank you for your cooperation.
Thank you for your patience. Oh, they are going to repeat.
So maybe
should I continue?
Talk over it now. We can hear you pretty well anyway.
Okay, so so we solve phonons, and like this is called density of state. It's computed over summation over the phonons at the wave vector and the phonon index. And the point of the computer simulation is that we have to discretize the calculation. So this summation can be done on a very sparse mesh in a reciprocal space, or quite a dense mesh in a reciprocal space. The thermal property can be computed, thermal property like heat capacity or free energy can be computed in a similar way. We have to integrate over on discrete points. And very tough to continue. Yeah.
And disaster prevention course on the DeskNet's information announced today. Thank you for your cooperation.
Yeah, so this is density of states and equation, and this is the result of the calculation with different discretization resolution. And with quite sparse discretization, we get the rough shape of density of states, but with quite precise mesh, we get a very smooth curve of the density of states. So, but the resolution that we need depends on the purpose. In fact, even for this quite sparse mesh, we can get enough information for some purpose like thermal property, but sometimes this shape is very important physically, so it depends on purpose. So we have to see the convergence, we have to check the convergence parameter that depending on our purpose. This is the difficult part of the computer simulation. And this is the design of PhonoPy code. I don't have so much time, unfortunately. So I just roughly say it's divided into two parts. It's a user interface and a computing engine. This part we implement mathematical equations, and these parts are divided by API. So we have a Python API used in Python, so we can use PhonoPy code from Python or interactively from Jupyter Notebook. This is the PhonoPy calculation workflow. We have crystal structure, and this crystal structure is relaxed using first principle code. So the point is that we have to run the PhonoPy and the first principle code alternately. And usually people handle this by hand. And run first PhonoPy, then run first principle calculation, again PhonoPy, and again first principle calculation, PhonoPy, something like this. And in between, first principle calculation is usually heavy calculation. We put it in a supercomputer to compute, and then we get the result, and then we collect those results, then put it into a PhonoPy and something like this. And but once we have a workflow engine, we can automate it. And now I use AIDA. Then we draw the AIDA PhonoPy workflow. This is the result of one calculation. And this is the graph of the result. This graph can be automatically generated by AIDA. And we have crystal structure as input, and automatically PhonoPy and BASP, this is first calculation code, launched, and finally we get automatically the result. And then once we draw the workflow for phonon calculation, we can apply it for many crystal structures. And this is not done by AIDA, but I also wrote some workflow engine before by myself, and I computed the phonons for 10,000 crystal structures. And this data is put in this website, and the data is licensed under the open data license, CC BY. But the data is provided not in a sophisticated way like what you are doing. Just those data are stored as an input file of the PhonoPy code. So you have to know how to use PhonoPy to get your interested data, like phonon band structure or some thermal property like heat capacity, because this is because you get a lot of information from phonon calculation. So once you have the force constant, you get the different kinds of result, not only the heat capacity or something like that. So I just put those information, and the phonon calculation is very cheap. Once we get the force constant, the computationally heavy part is first principle calculation part. Once it is done, it's very cheap. So this is a summary. I first explained about what is computer simulation, and then showed some mathematical modeling for phonons. And I noted something like discretization or convergence parameters that is quite important to know. And then software implementation, and showed some result performing a large set of computer simulations. Thank you very much. I'm very sorry for the announcement about the.
Don't worry about it. It was a small interruption. It was a little bit amusing too. So, you know, so thank you for the presentation. And it will be interesting to see, you know, how you took advantage of these infrastructures. Particularly curious about AIDA. But instead of asking all those questions right now, let's go on to the next presentation. And I think it's our final one before the panel, which should be Matthew Evans from Leuven, talking about Optimate. So if you're there and you can bring up your slides.
Can you hear me okay?
Yes, we can see you and hear you.
I have 2 mute buttons, and obviously I'd only done one of them.
Only 2. And we see your screen as well.
Fantastic. Great. Okay. Hello. Yeah, I'm Matthew Evans. I'm a postdoc at UC Louvain in Belgium. Most of this work was actually done while I was a PhD student at Cambridge, though. And as long as you don't tell anyone, I haven't actually finished that PhD yet. So I'm here today to talk about Optimate, which is a consortium and a specification for open database integration for materials design. So thank you very much for inviting me. I've been trying to go to a few talks. Obviously, it's a bit of a time difference here, but what I've seen has been very interesting. Okay, so what actually is Optimate? Well, I've already given you the one-line description, but really we're a consortium that's aiming to make existing materials databases interoperational, and we're doing that by developing a common REST API specification. And our progress so far, so it started at about 2016, and we've had 4 annual meetings since then, including sort of a virtual meeting this year. We've got about 50 or so contributors, so people who went to the actual workshops and also people who have directly written parts of the specification, which has now reached 20,000 words, which means it's a fairly hefty piece of work. I guess you don't want specifications to be too long, and it's kind of getting that way. And we also have 15 registered providers. So by that, I mean either individual research groups or institutions that have staked a claim that they will provide at some point an Optimate compliant API to some kind of materials database. So to kind of give you a feel for where these databases are and who they are, I've got a very low poly map here, and maybe if I just turn the pointer on, you can see we're mostly focused around the US and Europe at the moment. We'd love to get more people involved from other continents, especially sort of Costa Rica, and we've had some people from Japan in our meetings in the past, and it would be great to get some more people involved from over there. And really, we kind of captured quite a large section of the computational material science, the biggest sort of computational material science databases. So these are primarily crystal structure databases. Most of these store the results of density functional theory relaxations, as was sort of introduced by the previous speaker very nicely. So just to run through some of these, you've probably heard of most of them, I would guess. Going back to maybe the early 2000s, the COD, the crystallography open database, is actually an experimental database that stores about 500,000 experimentally determined crystal structures of inorganic crystals and MOFs and various other exciting things. Then you've got from the US these 3 big, I think these 2, the AFlow and Materials Project, are both Materials Genome funded, and then I'm not actually sure about the OQMD, but these are again big databases of density functional theory calculations. So AFlow, I think, has claims to have sort of 3 million or so structures. OQMD, we're looking at about 500,000. And then the Materials Project takes a more sort of slightly more curated approach, where they have just every known material rather than every possible hypothetical material. And back to Europe, 2 big projects: the Materials Cloud, which is closely linked to the AIDA workflow manager that was just mentioned, and also Nomad, together comprise a large section of crystal structures. So Nomad take a slightly different approach, where they ingest raw data files from sort of hundreds of different sort of simulation codes, and then store them and host them and archive them actually in a fair way. They're really sort of big on their fair implementation. And similarly, Materials Cloud is more for individual researchers actually to upload data sets to do with papers, but again have some sort of rich querying and rich formatting driven by the AIDA engine. And then I'll just focus briefly on this little dot around Cambridge, which is sort of my involvement, where in my PhD research group, we just sort of set up the classic computer in the corner of the office that runs a database. And we mostly focused on crystal structure prediction computationally, and sort of amassed a fairly modest library of about sort of 500,000 crystal structures there. But this is hopefully sort of showing you the difference in scale between some of these multi-million-pound projects and multi-horizon grant level projects, down to this sort of small federation of individual research groups. But what do we actually do? What actually is Optimate? Well, we released 1.0 in July this year, following our last workshop. And as I've already mentioned, at its core, it's a REST API specification for common access to crystal structure databases. And this kind of really solves a problem of each of those databases having their own REST API. Some are easier to use than others. But even if you wanted to just do a very simple query for, let's say, silicon dioxide crystal structures, you know, for N databases, there's probably N+1 ways of actually doing it. So, for example, the materials project, I think you would have to you have to query the chemical system directly. For A-flow, you have to be very picky about what is actually in the simulation cell. So if you want SiO2, you'll have to search for either Si1O2 or you know, every possible combination of Si2, O4, and so on to actually get the result you want. And this was sort of a cause of frustration for people when we came together to make this consortium, I guess, that we needed this, at least some agreement of how we should be able to filter through these databases. So that's, you know, what we've done by writing the specification. I say it's the human readable specification, so the sort of the ground truth is this large document, but everything is sort of based on JSON API. And we do have machine readable versions of it, thankfully. And this is enabling, I mean, I say 25 million crystal structures, that there's quite a lot of overlap in that Nomad, for example, have sort of eaten all the other databases and also serve them directly. But at least, you know, if you were to count the number of entries we serve, it's about 25 million across these sort of 14 different providers. And the little asterisk here means that some of them aren't quite as Optimate compliant right now, and some of them aren't quite public with their implementations yet, but we are really getting there and hope to have a paper out fairly soon. And the key that, or the sort of key thing that's interested me about this is that it's this sort of federation where we have a decentralized list of providers and discovery mechanisms built into the specification. So if you were to host an Optimate API, you provide your list of all the sort of sub-implementations your provider provides, and you can also link straight back out to all other providers. So we're hoping that it's sort of the network will grow organically, and we're hoping to make it as easy as possible for sort of small fish like my database was to actually join this bigger federation and get the benefits. And part of this, as part of this, we've been developing a fairly large set of tools that I'll talk about briefly, including how to sort of validate implementation in ways that go beyond just the definitions in the Open API schema. So sort of validating the actual underlying data of the implementation, that it actually makes sense and is high quality. And I'll kind of just rattle through some of the features of the actual database. So we obviously have to have a standardized representation for crystal structures. We have a well-defined grammar for filtering through them. We have these introspective endpoints that allow particular providers to actually extend the definitions we've already defined. And things like version negotiation and a fairly strict format on what we expect for a response from one of these REST implementations. But the actual data models themselves can be quite flexible. So as a specific example, the COD, the crystallography open database, doesn't actually store the positions of atoms in their database because they're sort of real crystallographers, as it were, that they store the like an irreducible representation and a list of symmetry operations. And if you ask for coordinates, they have to generate it on the fly. So for every query, you could be sort of lumping them with hundreds of hours of computing time to actually return some results. So everything is sort of built in such a way that there's lots of sort of should requirements in the specification, but most things you can get away with just not providing if you're not able to from your database. So I was going to sort of give you a quick zoom through the specification. I'm aware it's 1:20 in the morning here, so this might not be the most exciting thing, but just to sort of show you, we have a GitHub, we have lots of projects on GitHub as a consortium. There's links listed throughout these slides to show you that it's a real thing. I can actually show you the specification and hopefully show you that we have considered quite a lot of things. This isn't just a load of sort of dumb scientists trying to do data science. So you can just sort of look through the contents here. I'm not going to pick on anything in particular. Perhaps the actual definition of a structure is the most relevant. So I guess to sort of hark back to Zach's talk, I guess in some sense we have a 2-level vocabulary in that it can be easily extended. The introspective endpoints will provide all of this data, and it's only sort of advised that you provide it in the same format, I guess. So if you wanted to change a definition here, you could. What we don't have is any of the kind of enforcement of FAIR principles, and certainly don't have any formal vocabularies that we can link to, and I think that'd be a really nice addition in the future, actually. So just to sort of head back to where we were, we've also been developing, in fact, most of my work on this has been developing tools around this specification. So we have this Optimate Python tools package. So as you might guess, it's written in Python, it's open source, and really allows you to consume and implement Optimate compliant APIs, hopefully very easily. And I've said with no code, which is true with some caveats. Essentially, with just a configuration file and a database somewhere that with a backend that we support, you could host all your crystal structure data and be sure that the responses are all valid according to the specification, sort of very simply, actually, either just through a Docker image or with a bit of extra manual work. And this is all enabled by the 2 libraries underneath, Pydantic and Fast API. So just briefly, Pydantic lets you create data models using just Python type hints, which is a very sort of expressive way of writing them. Most of the actual sort of human readable specification is then stored in the descriptions of these models. And Fast API is another Python library built on top of Pydantic that lets you turn that straight away into a functioning REST API, essentially. So it's very sort of it's very quick to implement for us, actually. There's only 2 of us working on it. And it feels like kind of a very sort of grassroots approach to this kind of thing. So as I say, we have copies of all the data models from the specification. They're nicely annotated. You can explore them with like Swagger and other sort of open API tools. And they do this extra validation beyond the schema, as I mentioned. So for example, if you provided a crystal structure that had an elements field that said SI and O, yet you claim that the number of elements in the structure is 100, say, then obviously that'll be flagged up straight away, and that there's no chance that sort of will ever get out to the end user. And this is actually what generates the open API schemas that we have in the specification. And we implement the grammar as well, and support MongoDB and Elasticsearch at the moment. And we're hoping to sort of expand that to allow other future implementations to use different backends. And as I say, we also have mappers to existing formats. So for example, if you were to take a structure from a particular Optimate implementation, you could then convert it to all the sort of popular Python tools, so PyMatGen, ASE, and sort of for use elsewhere, and also to sort of write out a few standard file formats like CIF and PDB. So this package is actually directly used to host the materials project and the materials clouds implementation of Optimate, which I can maybe sort of show you in a second if I have time. And I think this is sort of one of the benefits of doing all this from the ground up, is that it, for example, I was able to use this for my implementation of my database as well. And really, I could then contribute back to a bigger project, and I could also receive sort of quite significant technical support from these much bigger institutions who have the sort of time and expertise to actually handle some of this stuff properly. So this kind of federation has worked really well for me personally, at least. And I think the approach of building tools, collaborative tools with everyone involved has been really good. Yeah, one other thing I mentioned is that we do also have the tools for validating remote implementations within this Python package. And if I just give you a link in a second, I can show you the kind of dashboard we have of all providers and how close they are to implementing the full specification at the moment. And because we have all the data models, you can also use this library to build clients. So here's just a link to one by my colleague Casper from EPFL, who's built this nice client that can ping all of the registered Optimate providers in one go and give you a nice sort of rich interface using Voila and Jupyter Notebooks. Okay, so just to quickly again run through the GitHub for this. So I say there's only 2 of us. That it's mostly been the work of Casper and myself, but quite a few other people have contributed in the past as well. And I just wanted to very quickly show how expressive these Pydantic models are. If I can use my touchpad properly. So just to look at the same example from the specification, I hope you can read this okay. Obviously, I can't really see my own screen. But if we look for the n elements model, you see it's nicely Python type hinted. We have the full description from the specification sort of automatically stuck in there. We have the extra metadata of the support level of this in the specification. So whether an implementation has to return it or is only required, they only should return it to actually give a full response. And then also we have these validators. So if I just find the first one. So again, hopefully you can read this. We have a validator for the anonymous formula field. So beyond just the sort of regular expression, you can add in the Open API schema. We can also do sort of more domain-specific validation. So checking that. So in the case of this field, it's an anonymous formula that has to represent or has to list the elements in order A, B, C by proportion. So SiO2 would be A2B. And that's really useful for querying sort of, give me all binary systems that have a ratio of 2 to 1, for example. But these have to have labels in the correct order and numbers in the correct order for this to actually work as a queryable field. So this is all sort of baked into these Python models as well. Okay. One other quick link to show is the providers dashboard. So this is our full provider list at the moment. It is just available as a JSON file as well, sort of statically hosted on GitHub pages. And just to give an example of what the validator can do, if we look at, say, the materials clouds offering of Optimate compliant databases. So the way they've done it, every data set that gets uploaded to materials cloud that used AIDA under the hood now has this sort of Optimate compliant REST API. And I think given sort of materials cloud's focus on FAIR as well, these are probably going to persist quite nicely and have their own DOIs and so on. And you can see that the validator in here it's not full marks across the board, but it's sort of close enough that if I was to go on one of these, I would know what to expect. So definitely not the time of day to be going through JSON directly in a presentation. But if we just quickly look at the info endpoint of this particular implementation, you can see it's sort of self-documenting in some sense. It provides links to its own documentation. You can see what the implementation they actually used and so on. And just to check that it actually works, we can also query for some structures. And thankfully this does work. And that was a randomly chosen implementation. And you can see they're actually using the same Python models here. So thankfully everything worked perfectly. I hear someone is unmuted in the background, so I guess that means I'm running out of time. I am very close to the end. I just want to sort of tell you what's next for this federation. So hopefully we'll release a 1.1 fairly soon. Hopefully we'll have a workshop in 2021. Probably still be virtual. The focus there is going to be on standardizing properties from calculations and also from experiments, and also on trajectories, which could include, for example, phonon calculations. We're looking at having a mechanism for sort of federated namespaces as well. So a few different providers can come together and say, we agree on a DFT vocabulary, say. Hopefully we'll improve the tooling, make things sort of more ergonomic for clients and also for implementations generally, and hopefully get more implementations on board as a result. I guess of most relevance to the RDA, we're looking at semantic interoperability. So a few of us have been looking at linking with existing European materials modeling ontology, and also seeing how we can sort of make things more Web 3.0, whatever we're up to now, beyond just the actual REST API. And a quick advert for there is a CCAM supported postdoc at EPFL. If you're interested in that, feel free to get in touch. But of course, yeah, we would love other people's contributions. So we have monthly meetings. The workshop is open to anyone who wants to attend. There's online forums and GitHub and so on that you can find online. I can come back to this later on if we have time for discussion. But I'd just like to end by acknowledging all the sort of partners on this project, all the people who have attended the workshops. I think, unfortunately, I was actually on the lake kayaking in this picture, so you can't see me there, but just to prove I was around, there I am. There's the entire provider list, and I'll just highlight Casper, who's worked with me on the Python tools quite heavily, my PhD supervisor, Andrew, who let me potentially throw my career away doing this rather than doing science, and my current boss, Gianmarco Levan. Thank you very much for listening.
All right, thank you very much. Very detailed. There's a lot going on there. So many questions. Now, I could say sadly, or I could say, I thought all the talks were excellent. We have actually run out of time in this session, which is a shame because I have a lot of questions for all of the speakers. I think we should, I've certainly committed to reaching out to each and every one of you at some level to explore this further. And so I just want to assure you that I know a number of my colleagues certainly, and I'm sure many people on the discussion here today want that as well. There is the Google Doc. Take a look at what people have written in there. Maybe we can get a conversation going, maybe set up some kind of chat, you know, Slack or whatever people's favorite modalities are these days. I would welcome people if they have any pressing issues that they just absolutely have to ask, but it is 8:30 on the East Coast. It's, I don't know, it's I think next Wednesday in Europe. I'm confused, and I think it's in the morning in Japan. So well done to everyone for making this work at this hour. So with that, I'm going to conclude this unless there are something pressing.
We just say great session.
Thanks, Jane. Good to see you.
It was outstanding.
That's a really great talk. Jim, could I just throw one thing out that if you're going to reach out to people, if there's going to be discussion, but like, let's try to host something and send an email to this group so everybody.
I think that's a really good idea, Dave. So
will listen in.
I will send out an email to everyone that's on here today. If you please put your email address in the Google Doc just in case, if you'd like to participate, and we'll set up another discussion where we can follow up on some of these questions. That seems like a very reasonable approach.
But just that way, if it fits anyone else's schedule, we can do it together.
Of course, we're going to have the same scheduling challenge.
Yeah.
But you know, what can you do?
Yeah.
So the people that organize it will have some leverage on what times they want to pick. Maybe we'll do 2 sessions. That was the original fantasy when we stood this thing up. We thought we were going to have an afternoon and an evening session, one for Asia and one for Europe, but RDA had other thoughts. So that's the way it goes. All right. Thanks again, everyone. We'll be in touch.
Good night.
Thanks a lot.
Good morning.
By the way, will the slides be made available?
Yes, please. If you have links to your URLs, please put them in the Google Doc.
Yeah.
That's sort of nominating yourself.
Will you make the slides available on the RDA site as well, or?
We could try. Sure. Once we have the URLs, there's no crime there, as long as no one.
I have the URLs for the slides, but if you could, you know, otherwise people have to go. I mean, it's okay to listen to the presentations again, but it'd be nice to have the slides accessible.
No, yeah, I meant just to the whatever, to some PDFs. That's right. Or okay.
Whatever people want to share. Thanks.
Exactly.
Great to see you guys.
All right.
Ray, you didn't see my note about your beard. Please see it. Bye.
Good night.
Likewise.
Right.
Thank you. Bye.
Bye-bye.
Thanks.